Greetings. So, we will continue our discussion on the variational principle, and this will be the concluding class to give the basics of the variational principle. And last time we did the not so simple pendulum, not the simple pendulum itself, but the not so simple pendulum, because simple pendulum is what you get when you make the approximation sin theta equal to theta. That is when the motion has to be on the arc of a circle. But then Huygens figured out that you put those choppers, and then if you have a cycloid pendulum, then you can have a pendulum with a periodic time which does not have to be calibrated every time you set the pendulum into oscillations, regardless of how far you take it away from the equilibrium. So, that is the cycloid Huygens pendulum that we discussed. And today we will discuss a few other aspects of the variational principle. So, let me remind you that this is based on the requirement that the action integral is stationary. It is an extremum, and action is the integral between two end points, the start and the finish, T1 and T2 of the Lagrangian, which is T minus V. And the condition that action is stationary, the necessary and sufficient condition that the action is stationary, is given by this equation, which is, as you can see, a second order differential equation. And this has this is then the equation of motion. It tells you, it describes how the system's description in the phase space evolves with time. So, it gives you the equation of motion. You have introduced the generalized coordinates because this equation is set up after you remove all the effects of the constraints. So, we work only with the independent degrees of freedom represented by the generalized coordinates. Their time derivatives are the generalized velocities, and the partial derivative of the Lagrangian with respect to the generalized velocity is what gives you the generalized momentum. And you can write the equation of motion in another equivalent form, which is the Hamilton's form, but these are two first order differential equations. Remember that there is a sign asymmetry which ensures that the Hamilton's equations of motion are also symmetric with respect to time reversal, just the way the Newton's equation is or the Lagrange's equation is. But never write the Hamiltonian as straight away as T plus V. Always set up the Lagrangian for the system first, okay? Always, as a rule, whether you are doing classical mechanics or quantum mechanics, always set up the Lagrangian first, then find out the Lagrangian will be in terms of the generalized coordinate and the generalized velocity, then find the generalized momentum as the time derivative of the partial derivative of the Lagrangian with respect to the generalized velocity. Okay. Then carry out the transformations from q dot to qp. Okay. These transformations are important, and only after you carry out these transformations can you describe the system in terms of q and p, and then in terms of q and p you can write the Hamilton's equations. And then of course in quantum mechanics you quantize the position and the momentum, you represent those by operators, and then you get the Schrodinger equation. So, always start with the Lagrangian, and this form of the Lagrangian is particularly convenient if you write it for a simple system. It makes this choice obvious that you can get the Newton's equation to be completely equivalent to the Lagrange's equation. So, it's nice because you obviously expect the same physics regardless of how you describe your state of the system and how it evolves with time. But the principles in Newtonian mechanics and the principle of variation are completely different. One relies on the cause-effect relationship, on the linear response of the system to a stimulus, which is the Newtonian dynamics, and it relies on the idea of force. It describes acceleration as proportional to the force. So that is the linear proportionality, which is fundamental to Newtonian mechanics. And the whole idea of force is dispensed with in Lagrangian mechanics. On the contrary, the formulation of the equation of motion is completely based on the requirement that action, which is this integral, is an extremum. It makes no use of the force, and this is really very strange but very nice, that you get exactly equivalent formulation of mechanics from these alternative principles. And it is a moot point to worry about which is more fundamental. Is it Newtonian mechanics which is more fundamental, or Lagrangian this thing? These are completely independent and completely equivalent formulations of mechanics. We often are happy to see that this gives you the Newton's form, but only because we have studied the Newton's equation a little bit ahead of Lagrangian mechanics. If only we had learned the Lagrangian mechanics ahead of the Newtonian mechanics, and there is no reason why we shouldn't. It certainly can, because it doesn't involve any additional mathematics than what is contained in Newton's equation. You still need the idea of a function, you need the idea of a limit of a function, the derivative, and so on. So once these ideas are there, you can develop the equation of motion either in the variational principle form or the Newtonian form, and they are completely equivalent, which is why it is a good idea to introduce Lagrangian mechanics at an early stage in education rather than wait for higher classes when it is often introduced. So the Lagrangian, I should alert you, is not unique. You can get the same equation of motion from some alternative Lagrangians. So here is an example that you can write a Lagrangian L prime, which is not L prime plus. I think I need a small correction here. This prime should not be here. So you can have a Lagrangian, and you can add to it the df by dt, where f is some function of just q and t, and you will get the same equation of motion. And you see it in alternative forms of Lagrange's equations. For example, you can carry out gauge transformations of the potentials, and you can get the same equation of motion. So the Lagrange's equation is actually a special expression of what is often called as the Euler-Lagrange equation, which is a more general formulation of the variational principle. When you apply it to a variational problem in mechanics, that is when you get what we normally regard as a Lagrange equation. But the formalism is very general, and it has a very rich history, which I will not really go through. But the major contributions are from Euler in this particular matter, in setting up the Euler-Lagrange equation. So let me quickly go through the Euler-Lagrange equation, which is a general formulation. And this formulation is applicable to some function or functional which depends on some variable xi, which is an independent variable, but it may also depend on another function of xi. So it may depend explicitly on xi, like a grandpa being happy or sad depending on how his grandchild does, all right, and that determines the grandpa's happiness, right. But the grandpa's happiness also depends on how his son's happiness depends on his child's happiness, all right. So there is an explicit dependence on how the grandchild performs, and there is an implicit dependence via how his son reacts to the child's performance in life in general, or exams or whatever. So, there is an explicit dependence, and so the explicit dependence on xi is contained over here. Then there is a dependence on xi via how phi depends on xi, and also in what rate phi depends on xi. How sensitive is phi to xi? Okay, phi depends on xi is a parameter. But how sensitive is it? Is it strongly dependent on the grandchild's performance, or is his son's happiness only weakly depends on that? Okay, so that's going to make a difference. So you have an explicit dependence, and then there is an implicit dependence, and the implicit dependence may be controlled by some control factor, which is gamma. And this gamma is something that you can vary. Okay, so this is the control parameter. So that is the nature of this function, and it can be the action that we have talked about in the context of mechanics, but it can be something else also. So you can apply. So this is very general formalism due to Euler, and you now have a dependence of phi on xi, but then it depends on a control parameter gamma. So how do you describe this? It depends on some value of phi for gamma equal to 0 plus another factor which is scaled by gamma. So this is the nature of dependence of phi on xi. So it's a very simple form that we have taken, that phi depends on xi through a control parameter gamma, which sort of provides a linear term in gamma which describes the dependence of phi on xi. So that's the kind of expression that we have, and we will consider this functional, which is an integral of psi over the parameter xi, over the variable xi, integral between two limiting values of xi. So in the case of our action integral, the limit is over the start and the finish, over the time t1 and t2. So here these are the two end values of xi1 and xi2, and we consider the variations in this interval and then ask, when is I an extremum, when is this stationary? Okay? So the principle of stationary functional is applied to this. So this is a very general formulation, and what we see in the Lagrange's equation is a special explicit form of manifestation of this principle of stationary functional. So these are the key relations. So this is how phi depends on xi. So this term is all obviously independent. It corresponds to the value that the function has at gamma equal to 0, whatever it is. And then whenever gamma is not equal to 0, so you've got some control parameter which you can change as you like, discretely or continuously. We will consider its continuous variation through small incremental values. And then our consideration, and this is the key point, so pay attention to this, that at the end points there is obviously no variation, because you know the start point and the fixed point and the end point in the xi space. Okay? So on the time axis it will be the start and the finish. Okay? But for a general function of an arbitrary variable xi, it is two end values, which is xi1 and xi2, and these values there is no change. So this is like solving a problem in mechanics in which you ask, if I take a piece of stone and throw it, and then what is its trajectory? You ask, what is its trajectory? That is a problem. So how would you solve it in Newtonian mechanics? You would set up the equation of motion, you need the force. So you know that the force is gravity, so you will put mg in your equation of motion. and integrate this equation twice, okay, to get the solution. And in the solution you will put the two initial conditions. Where have you thrown it from and at what speed did you throw it? Okay. What is the solution that you get? You get a parabola, right? And the reason you get a parabola and not some other trajectory, okay, you can think of alternative trajectories. You can think of any other trajectory. You know that, okay, it starts from here and it falls back over here, right? So, if x is the height, then it starts from x equal to 0 and returns to x equal to 0. And between the start and the finish, it can take so many different kinds of trajectories. But the manner in which you have solved this equation is by setting the initial conditions, and only one of these will give you the correct trajectory. Okay, all the other trajectories are incorrect. And the reason you get this is because the solution to the equation of motion gives you this quadratic dependence on time. So, that is what makes it a parabola, right? The equation of motion, Newton's equation of motion, has got a solution which turns out to be a parabola because of this quadratic dependence on time, and you get this from the initial position and initial velocity. Now, instead of initial position and initial velocity, if this question is posed in a different way, that you know that it starts with x equal to 0 and not the initial velocity, but instead of that you give the final position. So, one initial condition and one final condition. You are not giving two initial conditions. You are giving two conditions. You do have to give two conditions because the equation of motion is a second order differential equation. So, when you integrate it twice, there will be two constants of integration. So, you need that information. But this information is not provided through the two initial conditions of position and velocity, but initial position and the final position. So, you know that x is 0 at the base, both at the start and at the finish, and in between it can take, you can think of infinite number of paths. And now you ask, which path will the system take? And the solution better turn out to be this, which is what we got from Newton's equation, right? And you get this path. Now, you do not have the initial velocity, but you have to get this path using some alternative principle. So, this is the variational principle, that you get this path by solving the Lagrange's equation, which you obtain by demanding that action is stationary. That action is stationary. So, you determine what is the action along alternative paths, and there is one particular path which will give you the action to be stationary. So, that is the path which the system will take. So, this is answering the same question in mechanics, but using a completely different principle, that you have got one initial condition and one final condition, and at these extreme points T1 and T2, or in our arbitrary variable xi1 and xi2 space, there is no variation. These points are fixed. Okay? Like over here we said that, okay, it starts from here, it goes up, it comes back and lands here. Okay? So, these two positions are fixed, which means that we can use this when we solve the equation of motion. So, that information is available. So, now you construct this integral, and then you are going to demand when is this integral an extremum as you change the control parameter gamma, because the changes are coming because of the control parameter gamma, which you can change arbitrarily. You have got some control on that. Those are the ones which will give you alternative paths in space, okay, in the configuration space or phase space, or whatever is your parameter space. So, you will get alternative paths, and these variations, these alternative paths are coming not because xi is changing, but because gamma is changing. So, you find the partial derivative of I with respect to gamma, and notice that you have this term depends on gamma phi. So, the rate at which it changes with xi also depends on gamma, but this is an independent variable, this has nothing to do with gamma. So, the partial derivative of I with respect to gamma will involve the derivative of psi with respect to phi gamma and rate at which phi gamma depends on gamma coming from here, and then the partial derivative of this term with respect to del phi by del xi, which is what I represent as phi prime. But then you do not have to consider the variation of I gamma with respect to xi, because this term determines I, but it does not depend on gamma, that is an independent variable altogether. So, there are two terms over here, right. And then the important point is that at the extreme point, just like the example which I mentioned when you throw the stone, all right, you have one initial condition and one final condition at which there is no variation. So, the chi itself, which is contributing to the variation in phi, linearly scaled by gamma. So, chi at xi2 and chi at xi1 are both 0, there is no variation, those are the fixed points. So, now let us, since we have this relationship, then we can find the rate at which phi depends on xi, we need it over here, right. So, the rate at which phi depends on xi is now given by this relation. So, it depends on how the phi for gamma equal to 0 depends on xi, right. So, there is a variation in xi with respect to xi because of this term, and then there is a variation because of the second term, which is gamma times how chi itself will depend on xi. So, I will represent del phi by del xi as phi prime. So, prime denotes a derivative with respect to xi. So, there are two kinds of derivatives I am working with. One is derivative with respect to xi, and the other is over here, which is the derivative with respect to gamma. So, it is the derivative with respect to xi which is represented by this prime. So, now we have this relation. So, del phi by del gamma is chi, and you also need the del by del gamma of the derivative of phi gamma with respect to del xi, because these are the things which depend on gamma. This one does not depend on gamma. Okay. So, this term, the derivative of phi with respect to xi also changes because of the control parameter gamma, and this derivative is equal to chi prime. So, this is the relation that we got. Remember that the prime is derivative with respect to xi and not with respect to gamma. So, I have written the same thing, but I have introduced a little bit of color code just to help us keep track of the terms. So, phi prime itself is a derivative, right. Phi prime itself is a derivative which I have written here, and then there is another derivative with respect to gamma, and there is another term which involves a derivative with respect to gamma. So, these are the things which are changing because of gamma, because of the control parameter. So, here this is del by del gamma of phi prime, and phi prime itself is the derivative of phi with respect to xi. Now, these two derivative operators, there are two derivative operators here, one is del by del xi and the other is del by del gamma, and they are completely independent of each other. So, you can swap their positions. Okay. So, you swap their positions. So, you have del by del xi of del phi gamma by del gamma, and now you can go ahead and integrate this. So, the first term is written here just the way it was in the previous step, but here you have an integral of a product of two functions, one of which is a derivative. With respect to xi, it is just the derivative with respect to the very same variable over which integration is carried out. So, you know the total derivative, and that makes it very easy to integrate it in parts. Okay. it is, you integrate it in parts as a product of two functions, and you know the integral of one of the two functions because it is a derivative with respect to the very same variable over which integration is carried out. So, you carry out integration by parts of this term, and that is what gives you these three terms, of which this del phi by del gamma is nothing but chi, and this is at the end point xi1 and xi2, this is 0. Okay, this is what we said, that okay, you have got these 2 points fixed. So, chi at xi1 and chi at xi2 is completely fixed, and so this middle term, which is the difference of this particular product between the values at xi equal to 2 and xi equal to xi2 and xi equal to xi1, but then chi itself is 0 at both. So, it is 0 minus 0, which is also equal to 0 nicely, right. So, you get rid of this middle term. So, this is the term which will go to 0, because at the end points there is the chi's are fixed, they are not changing with xi over there, and that is what leaves you with only two terms, the first and the third term, which we have now combined over here. So, the left hand side is del I by del gamma, and then you have got the first term and the second term. I have extracted the common factor chi, and then you have got this term over here and this term over here, and the requirement that this is stationary, the principle of stationary functional, the necessary and the sufficient condition, no matter how you vary chi in between, okay, no matter how it is controlled in between. The necessary and sufficient condition that this integral is stationary, it is an extremum, is that the other factor in the integrand, which multiplies chi, must be necessarily 0. So, this is not exactly what gives you the Lagrange's equation when you identify psi with our Lagrangian, xi with time, and phi is the generalized coordinate, and the integral I itself is action. So, you see that the Lagrange equation is a special case of what we can call as a Euler-Lagrange equation, and this is the general principle of stationary action. It is valid for other situations in physics and mathematics, and it is based on one initial condition and one final condition rather than two initial conditions, okay, but it contains the same physics. So, we will see how it is useful by taking another example. We considered the cycloid pendulum last in our previous class, and we consider a bead on a circular hoop in a vertical plane. So, you have got gravity which is acting, of course, and if you consider an arbitrary position of the bead on the hoop, if you keep it like this, you know that it is going to slide down and settle down at the bottom, right. That is what you expect it to happen. But what if you spin it? If you spin it about a vertical axis, okay. Now, if you spin it, then you are going to have to solve the equation of motion, and how would you solve it? You will have to write the forces acting on it, and the forces, of course, are the gravity. But then there is also a force of constraint, because the bead can only slide on the hoop. So, the hoop will have forces of constraints. The bead is constrained to slide only on the hoop. The bead cannot leave the hoop and simply fall under, due to the Earth's gravity, okay. It can only be sliding along the hoop, okay. It is so because of this constraint, there is a force of constraint, which is the normal reaction. and then you have to set up the equation of motion, and that constraint is along the normal. It will be different at different angles of the bead, right? And it will have a component. Now this problem really becomes very complicated to solve, especially in inertial frame of reference. In a rotating frame of reference, you can insert a term which is an artificial force, which is the centrifugal force, and then write down the components of the centrifugal force along the vertical line, along the horizontal line, and along the normal, which is directed toward the center of the hoop, and then set it up, but it becomes really messy to solve. So we consider a frame of reference in which the x-axis is into the plane of the circle, all right, and the y-axis is in one direction and the z-axis is pointing in the direction of gravity. Okay, so it is a right-handed frame, but it has got a z-axis which is pointing downward toward the earth. So this is the frame of reference that we will make use of, and you can write the centrifugal force, which is m rho omega square, and then try to solve this equation of motion by resolving the centrifugal force along the tangent and along a line which is orthogonal to that, which is along the radial line. So you can set up the equations of motion and then solve it using Newtonian mechanics. But the normal reaction is anyway not doing any work on the bead. We can get rid of this constraint by setting up the equation of motion using Lagrangian mechanics, using the variational principle, by simply focusing on the independent degree of freedom, which is just the angle theta. That is the only thing that can really change. Okay, the bead is always going to be at a fixed distance from the center. It cannot escape the hoop. So that is the only independent degree of freedom, and we can set up the equation of motion with respect to the angle theta, which the hoop's position makes with, let us say, some reference line which is along gravity, which is along the z-axis. So in this coordinate frame of reference, the position of the bead is given by r times the unit vector along the radial line. Okay. So its velocity is given by the time derivative of the position vector, but the time derivative of the position vector is, the variation is coming only because of the change in ER. Okay. So this can only be along E theta and E phi in the spherical polar coordinates. R itself is not changing because it is always going to remain at a fixed distance, capital R. So this is velocity. So now you have got the generalized position and generalized velocity. So you can set up the Lagrangian as t minus v. Okay. And once you have the Lagrangian t minus v, you can take the appropriate partial derivatives, get the generalized momentum, partial derivative of Lagrangian with respect to the generalized velocity, and then the partial derivative of the potential with respect to q, right, and get the equations of motion. So you go ahead and get these partial derivatives. Okay. So that is quite straightforward, and once you have the partial derivatives, then you set up the Lagrange's equation, and now it has got a form which is also not so easy to solve, but it is not so hard to interpret the consequences. Okay, so you can get a lot of physics out of it by doing this simple analysis. So this is the equation of motion that you get, out of which m is constant in every term, so you can just strike it out. Okay. Phi dot is nothing but the angular speed with which the hoop is rotated about the vertical axis. So that is the speed of rotation. Okay, that is not the speed of rotation of theta, which is in the plane of the hoop, but this is the angular speed of the hoop itself about the vertical axis. So, this is phi dot, which is what I will call as omega, and in terms of omega you have got the equation of motion. Now, you have struck off the mass m, so it is completely independent of mass, and now from this equation, which is the equation for the second time derivative of theta, which is what tells you the acceleration. That is what an equation of motion is. It gives you the relationship between acceleration, velocity and position, right. So, if you analyze this equation of motion, even if you do not solve it really, you can get a lot of information, and our interest always is in finding, will the bead be in equilibrium at some point, and if so, what are the equilibrium points. So, what do you mean by equilibrium? Equilibrium is when the second derivative is 0, right. First derivative does not have to be 0, it is the second derivative. Okay. A body at constant velocity is also in equilibrium, a body at constant momentum, right. The first derivative is not 0, the first derivative of position is not 0, but if the second derivative is 0, then it means that it is in equilibrium. The position of rest, the inertia of rest and the inertia of constant momentum are completely equivalent, which is the Galileo-Newton first law of inertia. All right. So, the equilibrium is determined by theta double dot equal to 0, and now you can see that this is the expression which gives you what theta double dot is, which is the second derivative of theta. So, when will it be 0? It will be 0 whenever sin theta is 0. Okay. So, sin theta can be 0 when theta is either 0 or pi. So, theta equal to 0 in this geometry will be the point at the bottom and then the point at the top, right. So, those are the two equilibrium points, theta equal to 0 and theta equal to pi. So, these are the 2 points where the bead can be in equilibrium, but then we also discover that the bead can be 0 even when cos theta is equal to g over r omega square. For whatever value of theta and for whatever value of omega, if theta and omega are so adjusted, and that depends on the angular speed at which the hoop is rotated about this axis. So, depending on different angular speeds, this angle will be different, but you certainly can find an angle at an appropriate omega whenever cosine theta is exactly equal to g over r omega square. And if this happens, then again the second derivative of theta vanishes, and if that happens, then again you have an equilibrium position, and that can happen only above a certain speed. If the hoop is rotated at lower speeds, this cannot happen. It can happen only at a certain minimal critical angular speed. Why? Because cosine theta must be less than or equal to 1. So, omega will have to be above a certain critical frequency at a minimal angular speed. So, this is the critical frequency that you must rotate the hoop at. So, there are these 3 positions of equilibrium, and there is a critical frequency which is the angular frequency, which is essentially the speed of angular rotation of the hoop about the vertical axis, and these are the positions where the equilibrium can be found, where the bead can be in equilibrium. Below that critical frequency, the bead can be certainly in equilibrium only at the top or the bottom. Otherwise, there is a third equilibrium point which is also available to the bead, and this is not an information which is easy to extract from Newtonian equation of motion, but from Lagrange's equation we can get it so easily. So, let us examine the nature of the equilibrium, and to do that we consider a point which is slightly away from the equilibrium point. Okay. So, if the bead is at equilibrium at an angle theta, let us ask what will happen at a neighboring point which is slightly different from theta. So, that neighboring point is this equilibrium point theta 0, it is the difference between this neighboring point at the time t and the equilibrium point. So, let us ask what happens to this condition that you get from Lagrange's equation to this for how does it work with the neighboring point, and of course you need the sine of the angle, you also need the cosine of the angle. So, you determine sine of the angle at this neighboring point and you get a term which is in quadratic in delta, so which you can ignore to first order, right. You have a similar expansion for the cosine delta for the neighboring point, and you have you put the two together because actually what you have in this equation is a product of cosine theta and the sine theta. So, in the product you put all these terms and retain only the linear terms, remove the quadratic terms. So, if you remove only the linear terms, then you have this relation which has got fewer terms, all the quadratic terms in delta have been dismissed, quadratic and those which are even weaker than those. So, you can simplify these terms. So, there is no big mathematics or physics in this simplification, you just rearrange the terms. And notice that from these two terms which have been underlined, you recover the original condition at the equilibrium point, which is the theta 0. And at this equilibrium point, you know that these two terms must cancel each other, because these two terms will give you g over r minus omega square cosine theta 0, and this term vanishes at the equilibrium point. Okay, that is how equilibrium is defined. So, you are left with only this theta double dot and this term which is linear in delta. So, this is the equation now to be considered, and using this equation we analyze the nature of the equilibrium at the three equilibrium points. So, the first equilibrium point and the second equilibrium point, which is the bottom and the top, we know something about. We also anticipate that there is a third equilibrium point depending on the speed of the hoop, right. So, at the first equilibrium point theta 0 is equal to 0. So, the first equilibrium point is what I denote by the superscript 1, all right, and over here cosine theta 0 is equal to 1. So, I put it back in this equation, cosine theta 0 is 1. So, this term is cosine square, this term is cos theta. So, you get omega square minus twice omega square plus omega c square over here, which simplifies to this relation, and that means that depending on the relative difference between omega and omega c, okay, if omega is greater than omega c, this bracket will be positive. On the other hand, if omega is less than omega c, then this bracket will be negative. So, the second derivative is either positive or negative depending on the speed, whether is it above the critical speed or below the critical speed. So, slightly above the critical speed, it will be an unstable equilibrium, which is the point at the bottom. So, it will be unstable equilibrium above that critical speed, but below that critical speed it will be a stable equilibrium. Okay, so, that is the nature of the equilibrium, and we are able to get this information so neatly and so easily from the Lagrangian formulation. This is not something that we could have obtained so easily from Newtonian formulation. Okay, so, let us look at the nature of the equilibrium at the top, which is theta equal to pi. So, this is the second equilibrium point, which is denoted by the superscript 2, and here cosine theta is minus 1. So, you go ahead and put the value of cosine theta 0 equal to minus 1 in the equation in the first line, and the square of minus 1 of course is plus 1, but in the third term you have got cosine theta 0. So, you get a minus 1 multiplying omega c square, and that is an important term, because what it does is it gives you this relationship, and and essentially when you write it for the second derivative of theta, it is always positive, because the term on the right hand side involves the squares of the angular speeds, and they are always positive no matter what the speed is. So, omega can be less than omega c, it can be equal to omega c, or it can be greater than omega c. Irrespective of that, the right hand side is always positive, the second derivative is always positive, and you will always have an unstable equilibrium at the top. It will never be stable, okay, irrespective of the speed at which the hoop is rotated. What about the third equilibrium point? The third equilibrium point is when you have got this very critical balance between the angle theta and the speed, angular speed at which the hoop is rotated. So, over here you know that cosine theta has an upper bound. No matter what the angle is, it can never exceed 1. So, it is always less than or equal to 1. So, the angular speed will always have to be greater than the critical speed. So, you will not have any intermediate angle as an equilibrium point unless you have the speed rotated about the vertical axis above that critical angular speed, which is omega greater than or equal to omega c. So, that is a necessary condition, and you're guaranteed that omega must be greater than or equal to omega c. So, now you can put this condition over here, okay, and you when you write this, because cosine theta 0 is equal to omega c square over omega square. So, you put this value over here and then you simplify this, and you see that this is the second derivative of theta, which is going to give you the nature of the equilibrium. Is it a stable equilibrium or is it an unstable equilibrium, is going to be determined by the sign of the second derivative of theta. So, this term is omega c square minus omega square, and obviously below the omega c and above the omega c, this has got a different sign. However, the possibility of it being an equilibrium below the critical speed does not even arise. If it is at equilibrium at all, it has to be above that critical angular speed. Okay, so omega must be greater than omega c, which means that theta double dot has to be negative, and this will be a stable equilibrium. Okay, so it is an equilibrium above that critical speed, but then the nature of the equilibrium is stable. So, this is a very interesting physical conclusion that we have been able to extract by carrying out this analysis. So, at this critical angle, you will have a point of stable equilibrium above that critical speed. And notice that there is a stable equilibrium over here, but there is also a stable equilibrium over here. So, from one stable equilibrium, which is at the bottom, you can go to these two equilibrium points, and this is like bifurcation. So, instead of having just one, and in the next unit after this I am going to discuss the chaos theory, and that is where the bifurcation will become very important. The attractor becomes has two possible values instead of one. So, this becomes an important thing in chaos theory. So, we will consider another example which I will not work out in details. We are toward the end of this class, so I will only highlight the main points and let you work out the solutions. So, we consider a double pendulum, which is a pendulum attached to another pendulum the way you see it in the picture, but we will work with some approximations. I have shown these two masses as capital M and lowercase m, but then we are going to consider them as point masses. Okay. So, only for the picture I have drawn them as big pieces for you to recognize them to be different, okay. But otherwise we will consider them to be point masses. We will also assume that there is no mass in the rigid supports, okay, in the rods which are holding these masses, okay. There is no mass distribution over it, so they are practically massless, you consider that mass to be 0. And even with these approximations, these are gross approximations, this is obviously not a real system. But even with these gross approximations, this is not an easy problem to solve. So the length of the rods may also be different. So this length is Lm with this uppercase m, and this length is L but with a lower case m. So the lengths of the rods are different, the masses are different, and you can write the coordinates of the first mass, which is the uppercase capital M, the bigger mass if you like, okay, and then you can write the coordinates of the lower mass as well, and you can write it with reference to the coordinate frame which I have shown, which is the x axis going to my right, y going in this direction, and then z will be perpendicular to the plane, and it will be an arrow pointing toward me in the Cartesian frame of reference, right. So this is the coordinate frame of reference, and you can write the coordinates of the capital M mass and then the lower case mass, which is the smaller mass if you wish, are given by similar expressions, but then they are moved from here, this point, rather than from this point. So the x and y coordinates of this mass have to be added to get the coordinates of this. So that's the addition which has been done over here. So it is xm plus lm sin phi and ym minus lm cosine phi. So that's what you have done here. And now you have got the coordinates, you can get the velocities, because all you have to do is to take the time derivatives, right. So you get the time derivatives, the x dot and the y dot, and do the same for the lower for the lowercase m, which is the small mass if you like, right. So you write the coordinates of that and write the velocities of that, and now you have got the coordinates as well as the velocities. So this is the double pendulum. You can go ahead and set up the equation of motion. So you need the Lagrangian, which is t minus v. So this is the potential, right. So once you have the positions, you know what the gravitational potential is, because the gravitational potential depends only on the position. So we have got the positions of both the masses. So you get the potential for the whole system, and then you set up the kinetic energy term T by getting the velocities and then taking their squares. So you will get the T minus V. So you have got the kinetic energy term, and I will let you work this out, and you will discover that depending on the initial conditions, the motion can be absolutely bizarre, and this is another example of chaos that we will be discussing in the next unit. So once you can you can solve the Lagrange's equations, but the solution can become chaotic depending on the initial conditions. So this will be our subject for discussion in the next unit. What we are trying to answer is this question, not really this question, but this is often how it is posed, which is not how it should be posed, as to why does an object take a particular path, and you try to answer this question using different methods, Newton's method, Lagrange-Hamilton method, right. Then if you take some other situations like the Young's double slit experiment, okay, and then you do this experiment with light and you get interference pattern. You can do this experiment as Feynman suggested. At that time this experiment was not done, when Feynman suggested this in the early 60s. So this experiment was a completely thought experiment in Feynman's mind, but it brought out the foundation principle of quantum mechanics in a very beautiful and comprehensive manner. So you can answer this question using quantum mechanical formulation, which is the Schrodinger or the Heisenberg formulation, but I also told you that the Dirac-Feynman path integral approach also provides you with this solution. And if you go even in the theory of relativity, which is the general theory of relativity, you can use a similar variational principle, which you will see in the last unit we will do in classical mechanics, in which we will obtain the Schwarzschild solution to the Einstein field equation to describe certain results which can be accounted for only by invoking the general theory of relativity, which is the precession of the Mercury orbit. So, in all of this we have found that the variational principle comes in handy. So, it is a very powerful principle running through classical mechanics to quantum mechanics to general relativity. See its power and the canvas it covers. Okay? And the question that you are really answering is not really why a system takes the path that it does, but it answers what is the particular path taken by this system and how do you describe it. And this is what most questions in science really boil down to. And I had mentioned this earlier also, that means even when I toss this question, why does an object take a particular path, I said that this is often how the question is posed, but this is not really the right question to be asked. The right question to be asked is, how do you describe the path? The system takes a certain path according to the certain laws of nature, and we are asking, what is this law of nature? How do you formulate the law of nature which describes it accurately? You can answer everything by imagining that, okay, I think it is so because the color of this object is white or red and green, and nobody can disprove it, right? So, you can make a hypothesis, it can be your idea of a God or whatever, that okay, this is how the universe was created, and nobody can disprove it. But it does not tell us very much. So, science does not really try to answer this question, why does an object take a particular path? It tells you what is the path that the object takes. And it describes it very accurately, very scientifically, and it challenges that, okay, go ahead and test it. Do any experiment. And is the law that I am providing, the law that was provided by Galileo Newton or by Lagrange or Hamilton, is it violated by anything that you see around you? Is there a single experiment which can be done which violates this law? And if you find that yes, there is an experiment which violates that law, then it means that your theory is incomplete. It needs to be modified, it needs to be corrected, or it even has to be abandoned and you have to come up with a completely new theory. So, when you hit the limitation of the applicability of what you believed is the law of nature and it does not work out, then you have to modify the theory or even replace it by a completely new theory. So, that is how the theory of gravity due to Einstein ended up replacing Newton's theory. The quantum mechanics replaced classical mechanics, because you found experiments, observations which Lagrange, Hamilton, Newtonian, classical mechanics could not explain. But the variational principle turns out to permeate itself across classical mechanics into quantum mechanics in Feynman's path integral approach, and it permeates across Newtonian non-relativistic mechanics into Einstein's theory also. You see that it is applicable. So, thank you very much. If there is some question, we can discuss.